Let's take up adsorption isobar. Adsorption isobar, a graph between the amount of adsorbate adsorbed per gram of adsorbent and the temperature at constant pressure is called adsorption isobar. Adsorption isobar is the graph between extent of adsorption versus temperature at constant pressure. X over m represents extent of adsorption. X is mass of adsorbate and m is mass of adsorbent. So when we plot a graph between x over m versus temperature at constant temperature at constant pressure, the graph obtained for physical adsorption is the first one. It shows that extent of adsorption decreases with the increase in temperature, because as the temperature increases, the force of attraction between adsorbate and adsorbent, which is already weak, will become more weaker and desorption will take place and extent of physical adsorption will decrease. Next graph is adsorption isobar for chemical adsorption. In the case of chemical adsorption, X over m first increases with the increase in temperature and it becomes maximum at a particular temperature. After that, if we increase the temperature, extent of adsorption starts decreasing. What is the reason for that? In the beginning, we need some energy so as to overcome activation energy. But at high temperature, the bonds between adsorbate and adsorbent will start breaking and extent of adsorption will decrease. Next, we are taking adsorption isotherm. When a graph is plotted between X over m versus pressure at constant temperature, isotherm means constant temperature, it is called adsorption isotherm. Freundlich gave the following relationship between extent of adsorption and pressure. X over m is equal to K into P raised to the power 1 by n, where X is mass of adsorbate, m is mass of adsorbent, and pressure is P. K and N are constants which depend upon the nature of adsorbate as well as nature of adsorbent. At low pressure, X over M is directly proportional to pressure. That is, X over M is proportional to P raised to the power 1. See, in the beginning, X over M is directly proportional to pressure, so we get this dotted straight line, almost straight line, which is shown in dotted form. At high pressure, extent of adsorption X over m becomes independent of pressure. That is, X over m is directly proportional to P raised to the power 0. And this pressure after which the extent of adsorption becomes independent of pressure is called saturation pressure. At intermediate pressure, X over m will depend upon the power of pressure which lies between 0 and 1. That is, X over m is proportional to P raised to the power 1 over n, where n is greater than 1 and 1 over n lies between 0 and 1. X over m is equal to K into P raised to the power 1 by n. This is the first expression of Freundlich adsorption isotherm. On taking logarithm on the both sides of the first equation, we get log x over m is equal to log k plus 1 over n log p. This is the second expression of Freundlich adsorption isotherm. Expression 1 and 2 and the graphs are called Freundlich adsorption isotherm. Expression second represents a straight line. The slope of the line will be 1 over n, while its intercept on the log x over m axis will be equal to log k. This is the graph plotted between log x over m versus log p, and we get a straight line. The intercept cut on the y-axis is representing log k. Slope of this line, which is equal to tangent theta, is equal to 1 by n. Temperature. Adsorption is accompanied by evolution of heat, that is delta H is negative. So the rate of adsorption should decrease with the rise in temperature, because in exothermic process the rate of reaction decreases with the increase in temperature. It is found to be so in the case of physical adsorption, and effect of temperature on extent of adsorption is represented by adsorption isobar, which we have already discussed. Application of adsorption. Gas masks. You must have seen in coal masks. In the coal mines, gas masks are used by the coal mine workers so that poisonous gas they don't inhale, which may lead to the death. Production of high vacuum. Now, production of high vacuum, how we create, we take an adsorbent on which the gases get adsorbed, oxygen and nitrogen, and we get high vacuum. Removal of coloring matter from solution. The colored substance, if you heat it with charcoal powder, particularly animal charcoal, it will absorb the undesirable color from the solution and you will get pure substance. Humidity control. Humidity control can also be done by adsorption. For example, silica gel will adsorb water vapor and decrease humidity. Separation of inert gases can be done with the help of adsorption because different gases adsorb to different extent. Helium gets adsorbed to minimum extent because it has smallest size and least surface area. Xenon will adsorb to maximum extent because of highest surface area and more van der Waals force of attraction. So its extent of adsorption will be more. And also helium is most difficult to liquefy, whereas xenon is most easily liquefied. And all the gases which are easily liquefiable get adsorbed to more extent. Heterogeneous catalysis is based on adsorption. Reactants get adsorbed on the surface of catalyst, change into product. First, they form unstable intermediate, which readily changes into product. Deionization of water. Here we use resins which adsorb the ions present in water and we get deionized water. Softening of hard water. Calcium and magnesium ions are removed by adsorbing on the resins or ion exchange, particularly ion exchange resins, and we get soft water. Cleansing agents are also based on adsorption. In curing diseases, adsorption is applied. Adsorption indicators are used. We have discussed already. Fluorescein acts as adsorption indicator which gets adsorbed on the precipitate of silver chloride and imparts pink color to it. Froth flotation process is also an application of adsorption in which sulfide ores are concentrated. Sulfide ores are attracted towards oil and gangue are attracted towards water. Chromatographic analysis is based on differential adsorption. Next, we are taking catalysis. The phenomena in which the rate of reaction is altered, that is increased or decreased by the presence of substance, that is catalyst, is known as catalysis. If the catalyst increases the rate of reaction by lowering down the activation energy, we call it positive catalyst. And most of the catalysts are positive catalysts. But there are some catalysts which decrease the rate of reaction by increasing the activation energy. They are called negative catalysts. For example, acetanilide reduces the rate of decomposition of hydrogen peroxide. Catalytic reactions are divided into two types. First is homogeneous catalysis, second is heterogeneous catalysis. Homogeneous catalysis. When the reactants and catalysts are in same physical state, that is in the same phase, it is called homogeneous catalysis. For example, in lead chamber process for manufacture of sulfuric acid, NO gas is used as a catalyst. Now sulfur dioxide is a gas, oxygen is a gas, and catalyst NO is also a gas. That is why it is the example of homogeneous catalysis. Second example is hydrolysis of methyl acetate, which is catalyzed by H ion furnished by hydrochloric acid. So methyl acetate on hydrolysis in the presence of H ion give acetic acid plus methyl alcohol. Both the reactants and catalysts are in same physical state. This reaction is slow in the beginning, becomes fast later because acetic acid also furnishes H ion and concentration of H ion increases, therefore rate of reaction increases. Inversion of cane sugar in aqueous solution is catalyzed by dilute acid. Sucrose on hydrolysis in the presence of sulfuric acid gives glucose and fructose. This is an example of homogeneous catalysis because we are taking glucose solution and sulfuric acid, which is aqueous solution, is acting as catalyst. Why it is called inversion of sugar? Because in this reaction dextrorotatory sucrose changes into mixture of dextrorotatory glucose and levorotatory fructose, and levorotatory fructose has got more optical rotation, so the mixture of glucose and fructose is levorotatory. That is why it is called inversion of sugar. Molecular formula of glucose and fructose are same, but their structural formula are different. Glucose contains aldehyde group, whereas fructose contains ketone group. Heterogeneous catalysis. When the catalyst and the reactants are not in same physical state, that is not in the same phase, it is called heterogeneous catalysis. For example, oxidation of sulfur dioxide into sulfur trioxide in presence of platinum or V2O5. This process is called contact process. 2SO2 gas plus oxygen gas gives you 2SO3 gas in the presence of vanadium pentoxide. Vanadium pentoxide is a solid which is acting as a catalyst, whereas reactants SO2 and oxygen are gases. This is the example of heterogeneous catalysis. Second example is Ostwald process for manufacture of nitric acid. The first step in this is ammonia gas gets oxidized with the help of oxygen in the presence of platinum, which is solid, as a catalyst to form NO and 6H2O. NO is further oxidized to NO2 with the help of oxygen, and NO2 is dissolved in water to get nitric acid. Another example is vegetable oils which are liquid. If hydrogen gas is passed through vegetable oils in the presence of nickel solid as a catalyst, we get vegetable ghee. So hydrogenation of vegetable oils to form vegetable ghee is also example of heterogeneous catalysis. Decomposition of hydrogen peroxide liquid in the presence of platinum solid is another example of heterogeneous catalysis. Hydrogen peroxide on decomposition forms water and oxygen. Haber's process for manufacture of ammonia. Here iron is used as a catalyst which is solid, and molybdenum is used as a promoter. Promoter means that it increases the activity of catalyst. So nitrogen is a gas, hydrogen is a gas, iron and molybdenum both are solid. That is why this is the example of heterogeneous catalysis. Adsorption theory of heterogeneous catalysis. This theory explains the mechanism of heterogeneous catalysis. The first step is diffusion of reactants to the surface of the catalyst. Second step, adsorption of reactant molecules on the surface of the catalyst. And third step, occurrence of a chemical reaction on the catalyst surface through the formation of an unstable intermediate. The fourth step involves desorption of reaction products. Desorption means removal of adsorbed substance, which is called desorption. So desorption of reaction products from the catalyst surface and thereby making the surface available again for the mole reaction to take place. Last step is diffusion of reaction products away from the catalyst surface.